Let's consider a solution of acetic acid. So here we have some acetic acid, put that into some water, a little bit of it breaks apart because it is a weak acid, and then to that solution we add some sodium acetate. Sodium acetate is the exact same thing as acetic acid, just instead of the acidic proton, we have sodium. So the sodium is taking the place of the H+ that is normally let off into solution when it behaves like an acid. And so this molecule, the sodium acetate, is what we call a soluble salt, which means that it's going to completely dissolve. And not only that, going to completely dissociate because it is ionic. So every single last one of these sodium acetates that we put into solution is going to make some acetate ion. Now the key thing to realize here is that the acetate ion that the sodium acetate puts into solution is the same ion that is created when the acetic acid dissociates. It is in fact the conjugate base for this reaction up here. So by adding this source of acetate ion, what we've done is we have artificially jacked up this the concentration of the product, this particular product, in this equilibrium. This is going to have a significant effect on the equilibrium. This is what we call the common ion effect. So if there was nothing else in the solution, we would just have this equilibrium going on, and we could solve for the equilibrium just like we've done a dozen times at this point. But because something else is in the solution, and that something else is increasing the concentration of something that's involved in the reaction, that is going to have an effect on our equilibrium. So in this particular case, because we've jacked up the amount of one of the products, Le Chatelier's principle tells us that the equilibrium is going to shift to the left. Because if we artificially increase the amount of this, the equilibrium is going to try to get back to where it was before it was artificially changed, and so the only way it can do that is by consuming some of that acetate. So it's going to shift the equilibrium, reducing not only the amount of acetate, but also the amount of H+, since that's also on the right side of the equation. So, the common ion effect tells us the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So essentially we can keep some of these weak electrolytes from dissociating if we put something else into the solution that is going to have an ion in common with the molecule when it dissociates. So as an example of that here, we're going to calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar HF and 0.1 molar HCl. So we have two things in the solution. One of them is weak, the other is strong. The HF is weak, and the HCl is a strong acid. So the Ka for HF is 6.8 times 10 to the negative 4. So we know that the equilibrium that's going to exist is this equilibrium here. 6.8 times 10 to the negative 4 is equal to H plus times F minus over HF. If we go ahead and plug in what we know into an ICE table, we know we're starting with 0.2 HF, and we're starting with 0.1 H+, because that HCl, being a strong acid, every last bit of it is going to dissociate to make H+. And so we will have 0.1 of that, and we don't have any information about F minus, and so we'll just have 0 of that. Just like any other weak acid problem where we don't know any equilibrium stuff, we're going to have minus x, and plus x. If we apply those and use the x is small assumption, what we're going to end up with is this. 6.8 times 10 to the negative 4 is equal to 0.1 times x over 0.2. And if we do that math, we get 1.4 times 10 to the negative 3 is equal to x. And if we plug that back into the values from the equilibrium, or from the ice table, I should say, we find that F minus is 1.4 times 10 to the negative 3, because it was just equal to x. And the concentration of H plus that started at 0.1, when you add 1.4 times 10 to the negative 3, it's still just 0.1. Like, that would be technically 0.1001, which, based on our sig figs, we couldn't include. We would have to cut it out. And so it is still just 0.1. So then if we were to find the pH of that, it's just 1. Because the negative log base 10 of 0.1 is 1. All right. So the common ion effect here is something that is very, very useful. It has a really strong impact on the dissociation of weak acids and bases, and we're actually going to take advantage of this common ion effect in the next topic that we're going to cover here in this chapter, which is buffers. Buffers actually take advantage of the common ion effect to try and control the pH of a solution. So we'll talk about buffers in the next video.